We're now going to begin section 8.4, where we'll talk about complex numbers in trigonometric form. Recall that in Math 126, we learned about complex numbers. We're now going to learn about complex numbers in light of the trig functions. First, let's review the complex plane. The complex plane gives us a way to plot a complex number. For example, if your complex number was 3 plus 4i, then recall that we refer to the 3 as the real part of the number, and the 3 is plotted along the real axis, which is like the x-axis from an algebra class. The 4 is referred to as the imaginary part because it is attached to the I, and the 4 is plotted up what is normally referred to as the y-axis, but in this case will be the imaginary axis. So using the complex plane, using a real axis and an imaginary axis gives us a way to plot our complex numbers. We're going to begin our examples by finding what is referred to as the magnitude of a complex number. The magnitude of a complex number is essentially a measure of the distance from the 0, 0 complex number, which lies at the origin, to the complex number that we're talking about. So if we were to measure the distance from 0, 0 to 3 plus 4i, we would have the magnitude of 3 plus 4i. Now our formula for finding the magnitude is essentially the distance formula from algebra. So we're going to take the square root of a squared plus b squared, and that is going to be our magnitude. And note this symbol that we use for magnitude looks like an absolute value. And we do this to remind ourselves that magnitude is always positive. So let's take a look at an example. I'm going to write my formula here so I don't forget. So the magnitude of a complex number is the square root of a squared plus b squared. So our first example is the complex number negative 2 plus 5i. So in this problem, our a value is negative 2 and our b value is 5. And so we're going to plug into our formula to calculate the magnitude. So we'll have a squared, which will be negative 2 squared, plus b squared, so 5 squared. When I square the negative 2, I'm going to get positive 4. When I square the 5, I'm going to get 25. Adding them together, I get the square root of 29. So my magnitude for my complex number, in other words, the distance from 0, 0 to the point that represents the complex number, is the square root of 29. For our second example, we have 1 minus 3i. Again, the a value is 1, and the b value is going to be negative 3. So plugging into our formula, we'll have a squared, so we'll have 1 squared, plus b squared, so we'll have negative 3 squared. Squaring the 1 gives me 1. Squaring the negative 3 gives me positive 9. And so my magnitude will be square root of 10. So again, the distance between 0, 0 and the point 1 minus 3i will be the square root of 10. We're now going to talk about graphing regions instead of points in the complex plane. Our first example asks us to graph the region defined by, and this notation sometimes is a little difficult to understand. This is saying all z, so all complex numbers, okay, so that's this part, all complex numbers. This line we read as such that, remember that the absolute value symbol around the z references the magnitude, so such that the magnitude is less than or equal to 1. And so you can see that in our picture here, but let's make sure that that makes sense to us. So if I pick a complex number on the outside of this circle, say for example right here, and I look at the magnitude of this complex number, I'm just going to call this z. Remember that the magnitude is the distance from the complex number back to the 0, 0 point. So the distance in between these 2 points is the magnitude. Now the scale in this graph is 0.2. So we have 0.2, 0.4, 0.6, 0.8, and 1. So the distance between those 2 points is 1. If I choose another point, say I choose this point, and look at the distance between 0, 0 and this point, again, 0.2, 0.4, 0.6, 0.8, 1. And so the magnitude of that complex number would also be 1. And so if we do that all the way around and connecting those points, we see that we get this circular region where everything inside would have a magnitude less than or equal to 1. For our second example, and this one is a little bit more complicated, the problem says that we want all the complex numbers, okay, and so this is how they've written it this time. Instead of just writing a z, they've written a plus bi, so this is just simply saying all the complex numbers remember that the line indicates such that the absolute value of z is the magnitude is less than or equal to 1. So if we were looking just at this part, this is the same as part A and would have produced the same graph as what we have here. Okay, and then they've put an and in between, which means that they have to meet both conditions. And so they've said that the b has to be greater than or equal to 0. Well, remember the b is your imaginary part on your number. So the imaginary part of the number, which runs up and down the y-axis, has to be greater than 0. And so that's only going to happen for the top half of the circle. So remember that this is a b value of 1i, and this is a b value of 2i, and 3i, and so forth. If we come down on the bottom part, we would have the negative I values. So negative 1i, negative 2i, negative 3i, and we don't want those. Okay, so these are, I don't want that to look like a negative, these are the positive I values, positive 1i, positive 2i, positive 3i, those are the ones we want to include. We do not want to include the negative ones, and that's why the bottom half of the circle is not shown for this example.